Let's continue our discussion next with this example. Here you see these two sets A and B. A is the set of all real numbers from which this 3 divided by 5 has been removed. And B is the set of all real numbers from which 7 divided by 5 has been removed. And then two functions have been defined. F from B to A, given by this formula. F of x equals 3x plus 4 divided by 5x minus 7. You can see why we need to remove 7 over 5 from R in order for B to be the domain of F. That is because if x has this value, then 5x minus 7 becomes 0, and we don't want that because that's the denominator. And another function g, but this one is from A to B, and the rule, the formula defining g is this: g of x equals 7x plus 4 divided by 5x minus 3. So here also, in order to have a non-zero denominator, we have removed 3 divided by 5 from the set of real numbers, and that became the domain of g. Alright, now what do we do with these two functions? Let us define another function. Let S be any non-empty set on which we define a function is. On which means S will be the domain of is and also its codomain. And the definition of is is very straightforward. Is actually does not change anything. You take any element x from S, is gives that element back. Is of x is defined to be equal to x, and this is actually called the identity function on the set S. Now, this is what we have to show. We have to show that f composition g equals the identity function on A, and g composition f is the identity function on B. You see, one thing is immediately clear. What is the domain of f composition g? By the definition of composition, that is equal to the domain of g, and domain of g is A. And what is the codomain of f composition g? That should be the codomain of f. That is also A. So that means this is a function from A into A. IA is also by definition a function from A into A. So it makes sense that we ask whether they are equal. So to prove that they are equal, you just have to calculate f composition g at any element x of this set. If you get x back, then your job is done. Similarly, we have to prove this one. So we start the solution also by mentioning that fact. Clearly, both the identity function on A and f composition g map A into A. That means both these functions have A as their domain and also A as their codomain. Now we take any element x in A and calculate f composition g of x, which by the definition of composition is f of g of x. Now this is what g of x is: 7x plus 4 divided by 5x minus 3. And what is f? F is 3 times the input plus 4 divided by 5 times the input minus 7, because the input itself is this. So this is how things are coming. Now we have to simplify this entire thing. So we do the simplification in the next step like this: 3 times 7x plus 4 plus 4 times 5x minus 3 divided by 5x minus 3, and in the denominator 5 times 7x plus 4 minus 7 times 5x minus 3 divided by 5x minus 3. So in the next step, obviously these two 5x minus 3's will cancel each other, and the numerator will be this: 3 times 7 is 21, 21x plus 12 plus 20x minus 12, and the denominator would be 5 times 7 is 35, 35x plus 20 minus 35x, and minus will give you plus 21. So you can see that here 12 and minus 12 cancel out. and you have 21x plus 20x, which is 41x. In the denominator, 35x and minus 35x cancel out, and you have 20 plus 21, that is 41. So after cancelling these 41s, you are left with x, which however is equal to IA of x, because IA does not change any element of A and x is an element of A. So this way you find that the F composition G image of x is the same as the IA image of x. That is why these two functions are equal. So we write the conclusion, hence F composition G is equal to the identity map IA on the set A. And the second half is also similar. Both the functions G composition F this time and the identity function on B map B into B, which you can check. You can go back to the definitions of F and G and see what G composition F is. I mean, from which set to which set it is a mapping. So then we have to show that they agree at every point of B. That means at every element of B, they have the same image. So accordingly, we take any element y in B and we start our calculation with G composition F of y, which by definition is G of F of y. So in the next step, we write what F of y is, and that is 3y plus 4 divided by 5y minus 7. And then G of this is 7 times this plus 4 divided by 5 times this minus 3. Okay, you can go back and see the formula for G. And then in the next step, actually we have skipped one step here, namely that step where we would write this divided by 5y minus 7 and this divided by 5y minus 7, because that 5y minus 7 ultimately will vanish, so we did not write that. So instead we are having 7 times 3y plus 4 plus 4 times 5y minus 7, and in the denominator we have 5 times 3y plus 4 minus 3 times 5y minus 7, and now we can continue. So the next step will be this. 7 times 3 is 21, 21y plus 28. 7 times 4 is 28 plus 4 times 5 is 20, 20y minus 28. And the denominator is 5 times 3 is 15, 15y plus 5 times 4 is 20 minus 3 times 5 is again 15 minus 15y, minus and minus will give you plus 21. So after you go through the cancellations, this is what you are left with. 21y plus 20y is 41y, and in the denominator you have 20 plus 21, which is 41. So it's just like the previous calculation. So you get y, and this is equal to IB of y. Note that this is not IA because y was originally chosen from B. So you cannot apply the function IA on y because it's not necessarily an element of A. So that is why this is IB of y. And that is why, because these two functions, because this is what we started with, right? G composition F of y, that is equal to IB of y. So these two functions agree at every element of B. That is why they are equal. This next example is theoretical in nature. Here we don't have any concrete function. Instead, two 1-1 functions are given. F, which maps A into B, and G, which maps B into C. Both of them are 1-1, injective. Then we have to prove that their composition, G composition F, which maps A into C, is also 1-1. That is also injective. It's actually a result. So this is the solution. What is it that we have to prove? We have to prove that G composition F is 1-1. So you can use either one of the two equivalent ways of doing it. Here, actually both are equally easy, but we have chosen this way. So what we did here, we took any 2 points x1 and x2 in A, the domain of this composition, such that their images are equal under this function G composition F. This is our assumption. G composition F of x1 is equal to G composition F of x2. which just means this g of f of x1 is equal to g of f of x2. Now it is given that g is 1, 1. And you see that these two g values are equal. So because g is 1, 1 and two images are equal, so the inputs must also be equal. And that is why, since g is 1, 1, we get f of x1 equal to f of x2, because those are the inputs for which these two g values are equal. But then you can apply that same argument to this equation, which says that the f images of x1 and x2 are equal, and it's given that f is also 1, 1. So the inputs must also be equal here, and that's how you have x1 equal to x2. But this is what we wanted to show. You started by assuming that the G composition if images of x1 and x2 are equal, and you have managed to show that then the inputs x1 and x2 are also equal. That is why G composition F is 1, 1, that means injective. This next example is also similar, but this time instead of 1, 1 we have the onto-ness property. Again we have two functions f and g such that f maps a into b and g maps b into c, but actually they are onto. Then we have to prove that their composition is also onto. So in this one we have to prove that this composition is onto, and for that we would choose any element in the codomain and show that that is the image under this function of some element in the domain. So we have to find that some element. So let Z be any element in the codomain C. Now note that C is also the codomain of G, and it's given that G is onto. So this Z must have come from some element in B via G, because G is onto. And that is why we write like this: since G is onto, there exists Y in B, the domain of G, such that the G image of Y is this chosen element Z. So this Y exists because G is onto, and Y exists in B, the domain of G. But B is the codomain of F, and now you have an element Y in B. And it's given that just like G, F is also onto. So this Y also must be the image of some element in A under the function F, because F is onto. So that is why we write like this. But F is also onto, so there exists an element X in A such that Y is the F image of X. But then if we combine these two things, what do we get? Say you again start by writing Z, which is your G of Y, but Y is F of X, so that way you find that Z is equal to G of F of X, which however by the definition of composition is G composition F of X. So have you not found what you wanted to find? Yes, you started by choosing any element Z in C, which is the codomain of G composition F, and you wanted to find an element in A whose G composition F image will be this Z, and that is what you have found exactly, and that element is X whose G composition F image is Z, and that's why G composition F is onto, because every element in its codomain is appearing as the image of some element in the domain under this function, and that's it. Now before we see the next example, let us summarize what we have seen in these last two examples. We have two functions f and g, so that their composition G composition F can be formed. And what was the first one? The first one tells us that if both the functions are 1, 1, then their composition is also 1, 1. And the second example, the previous one, tells us that if both of them are onto, then the composition is also onto. What is the implication of this? The implication of this is that if f and g are both bijective, that means 1 1 as well as onto, then their composition is also bijective. This is a very important result, and its importance you will realize later on in higher mathematics. But now in this next example we ask the converse question. Converse question means, let's just see what this says. Again you have the functions f and g, f maps a into b and g maps b into c, and they are such that the composition is 1 1. Okay, it's not given whether the functions themselves are 1 1, it's however given that the composition is 1 1, and in fact that is the question. Is it then necessary for both f and g to be 1 1? That's what we have to answer now. And the answer is no. It's not necessary for both f and g to be 1 1. They may be, but they may not be also. Let's see that here. Let us consider this function f from this set 1 2 to the set 1 to 3. And what is the definition of f? F maps 1 to 1 and 2 to 2. And another function g, which is from 1 to 3 to 1 2. And this is the definition of g. G of 1 is 1, g of 3 is also 1, and g of 2 is 2. Alright, for these functions, what is the composition, g composition f? Instead of writing things, let us see everything in this diagram itself, the arrow diagram. So this is your function f, which maps 1 to 1 and 2 to 2. This is the domain of f, and this is the codomain of f. What about g? G maps 1 and 3 both to 1, and g maps 2 to 2. Alright, now what will g composition f do? That is very easy to see from the diagram. G composition f maps 1 to 1 and 2 to 2. There is an intermediate thing, but ultimately what the elements are to which it maps, this 1 and 2, they matter. G composition f maps 1 to 1 and 2 to 2. So is it a 1 1 function? Yes, it is a 1 1 function, because it is mapping distinct elements to distinct elements. So G composition f is 1 1. However, both f and g are not 1 1. F is 1 1 because distinct elements are going to distinct images, but g is not 1 1 because of this. 1 and 3 are distinct inputs, but the output is same, it is 1. So it's not necessary in the other direction. And then in this next example, we have the exact same thing. The only difference is that here now we have onto-ness. Again we have our f and g as before, but this time g composition f is given to be onto, and the question is similar. Then is it necessary for both f and g to be onto? And the answer again is no. And magically that exact same thing can be taken as your solution. Let us see how. So we already know what these things are. Now we just have to see if G composition F is onto this time. Is it onto? Yes. You take any element in the codomain of G composition F, which is C, that is this set. Say 1. Is 1 coming from somewhere via the function G composition F? Yes. And that somewhere is 1. It is coming from 1. 1 is the image of 1 under G composition F. What about 2? Yes. 2 is the image of 2 under G composition F. So by the definition of onto-ness, G composition F really here is onto. Are F and G both onto? No. This time G is onto, because every element in the codomain of G is coming from somewhere in the domain of G. 1 is in fact coming from 2 places, although 1 is enough. I mean 1 place is enough, and 2 is also coming from 1 place. F however is not onto. because 3 is not coming from anywhere. 3 is not an image under f of any element from here. So it's not necessary for both the functions to be onto either, even when the composition is onto. And with this, let me just end this video. There are a few other examples here, and in the next video we are going to, slowly we are going towards the notion of invertible functions and their inverses, with which this section will end and then exercises will start. So see you in the next video with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.